this bond, and you will get a new molecule plus another radical. Now, if you look at that, say that's not going to be very productive, because you convert one weak bond into another weak bond. You're not going to gain much energy. So this is a process that might occur, but it's not really a very useful process. Certainly is not going to lead to anything stable. The other possibility is that this molecule, this radical, says, okay, I want to make a strong OH bond. By pulling off, by transferring a hydrogen atom from the alkene to the and that reaction creates then an alcohol, and that's a strong bond. It's a very strong bond. So this is energetically quite favorable. Plus a carbon with an unpaired electron. And we call this an allyl radical. Okay? So there's two choices. First one doesn't really lead anything. The second one, when that reaction takes place, you form a strong bond, and you can start to go to tables and say, and look at bond strengths in tables, and does this make sense? And if you look at tables, you'll find that this bond, and I know the numbers better in kilocalories, so you have to excuse me for that. I just multiply by 4.2 to get joules, kilojoules. This CH bond is, the OH bond is about 110 kilocalories per mole. And that bond here is only about 85 to 90. So we're breaking a fairly weak bond, making a stronger one. The other CH bonds here, the bond strength of that carbon, that bond is about 110 kilocalories. So the hydrogens that are joined to the double bond, they are held really tightly. It's this bond, these bonds here, these CH3 bonds are the weak ones. And then you say to yourself, well, why is it like that? What's special about these allylic CH bonds, and why are they weak? And the reason, one of the ways, the best way to explain why are they weak is to say, what's the structure of the product? If the product is a reasonably stable structure, then we can say that's why, it doesn't take so much energy to get to it. So let's look at the structure of the allyl radical. And this one, it really is fairly satisfying to say it makes sense that the electrons are delocalized, because in an allyl cation we have, again, we have these 5 hydrogens that are sitting there. We have, after we broke that bond, we have an empty, we have a p orbital with 1 electron in it. The double bond has 2 p orbitals, or a pi orbital with 2 electrons in it. And surely you could say, I don't know, these, this is symmetrical, but there is an equal amount of unpairedness in either direction. So this is there's certainly the electrons are certainly distributed evenly across the system, and we basically can draw this now like this with a partial double bond and an unpaired electron. Or easier and more useful is to say this is a double bond with an electron at this stage, and we can then move the electrons over, and we would have them there. So it's really the same kind of picture as we had with the allocation, except instead of having 2 electrons in here and a positive charge, we have now 3 electrons, and the species is neutral. There's no charge associated with this whatsoever. So, to make this to sort of focus again, what has happened so far? So far, we created an alkoxy radical. We transferred an allylic hydrogen to the RO to form ROH, and created or generated an allylic or allyl radical. That's what we've done so far in this sequence. Looks like a lot of words for a couple of simple reactions. So at this stage in the reaction mixture, the reactive species is something that we can draw like that. That's the reactive species right now in the reaction mixture. We haven't done anything. We looked at the possibility of using the succinimide, but we didn't use it until now. So maybe it's time now to take the succinimide, the N-bromosuccinimide, and now to transfer again an atom to a radical. And now we're going to transfer the bromine. Now we're going to make a carbon-bromine bond. Pretty decent bond. It's not nearly as weak as the oxygen-oxygen bonds or nitrogen-bromine bond. So if we transfer just bromine to here, we will get a nitrogen radical. We're going to gain energy by making a stronger bond and breaking a weaker bond. So drawing that sort of sequence with the fishhooks, the result of that is now